In the Mediterranean summer of 1943, the sky over Sicily was not a stage for heroism, but a constrained volume where altitude, heat, and air density turned every maneuver into arithmetic. Operation Husky forced fighter combat into a corridor that began high over the inbound sea lanes and ended low over dust, flak, and burning fuel farms. The episode that matters here is tied to a documented pattern of P-38 Lightning tactics during the Sicily campaign, when American pilots repeatedly entered fights from steep dives that many instructors considered mechanically unsound because the aircraft's high-speed control behavior could degrade without warning. The technical anchor was compressibility onset. In a steep dive, the P-38 could approach a regime where airflow over the tail reduced elevator effectiveness, and recovery demanded altitude that the tactical situation often refused to provide. The Lightning carried its contradictions into every engagement. It climbed well, accelerated cleanly, and it retained energy in the vertical, but it was also long, heavy, and sensitive to how speed translated into control feel. A pilot who wanted a safe intercept preferred shallow geometry, because shallow geometry preserved a recovery margin even if the aircraft stiffened. Yet over Sicily, the intercept problem was rarely clean. Luftwaffe fighters and fighter bombers came in low and fast, using coastline clutter and ground haze, and they often forced American pilots to trade time for position. That trade sharpened into a single constraint that shaped decisions: closure rate. If the attacker failed to generate enough closing speed quickly, the target reached cover, merged with escorts, or vanished into the broken visual background that made tracking unreliable. In that environment, the dangerous dive entry was not a stunt. It was a response to delay. AP-38 pilot who rolled inverted and dropped nearly vertical could convert altitude into speed so quickly that the engagement window collapsed to seconds, not minutes, denying the opponent the time needed to recognize the threat, choose a brake direction, and coordinate with a wingman. The technical anchor was time to impact. A 10-second reduction in attack time mattered more than a minor increase in firing accuracy, because it changed whether the defender could even initiate a coordinated defensive turn before the attacker's guns were already in range. Training doctrine had reasons to resist this. At high speed, the Lightning could become reluctant in pitch, and the pilot's instinct to haul back harder could deepen the trap by increasing drag without restoring authority. Over water, that could be fatal. Over Sicily, it became worse, because combat often began high but ended near the ground, and recovery space disappeared behind the urgency to stay with the enemy. The technical anchor was minimum recovery altitude. A dive that demanded 3,000 feet to recover safely could become unrecoverable if the pilot delayed pull-out by even 2 seconds, because the lost altitude arrived as a single irreversible deficit. But steep entry produced a second effect that mattered more than drama. It forced the fight into a vertical sequence where the Lightning's mass worked as a weapon. The aircraft was not a tight-turn fighter at low speed. It did not want a dogfight in a flat circle. A pilot who tried to copy the turning habits of lighter single-engine fighters could bleed energy until the Lightning became a target rather than a hunter. The steep entry avoided that trap by shaping the first merge. The technical anchor was energy retention. When the P-38 entered fast and exited fast, it preserved a speed reserve that could be converted into climb or separation, while the defender, forced into a hard brake at lower entry speed, paid an energy penalty that was difficult to repay. Over Sicily, that penalty mattered because the environment punished prolonged turning. The air was hot. Engine temperatures rose. Radiators and intercoolers were not theoretical systems. They were limits. A pilot who stayed at high power too long, too low, and too slow risked overheating, and overheating turned pursuit into forced disengagement. That reality made brief, violent attacks more viable than long, elegant chases. The technical anchor was thermal margin. If coolant temperature approached a critical limit, the pilot's tactical choices collapsed because the aircraft's engine could not be commanded to sustain the fight, no matter how much willpower existed in the cockpit. German fighters operating from Sicily and southern Italy brought their own constraints. They were often tasked with defensive interceptions on limited notice, frequently lifting off under the pressure of Allied bombardment and operating inside tightening fuel margins. Fuel margin is not a footnote. It is a leash. A fighter that can fight for 20 minutes instead of 40 minutes is not simply less flexible. It is structurally forced into shorter engagements, earlier withdrawals, and riskier decisions near the end of every sortie. The technical anchor was fuel endurance. When endurance drops, a pilot becomes more willing to take immediate risks to force a result because the option to reset and re-engage no longer exists. The steep dive entry exploited that. It was a way of imposing tempo. When an attacker arrives in a near-vertical plunge, the defender's decision time compresses, and compressed decision time increases error rates even amongst skilled pilots. The defender may brake too hard and stall. The defender may brake too shallow and remain in the gun sight. The defender may brake in the wrong direction and expose the aircraft's belly. These are not moral failures. They are outcomes of human reaction time operating inside a shrinking time budget. The technical anchor was reaction latency. At combat speeds, a 0.5-second delay is not a small hesitation. It is hundreds of feet of lost separation. There was also a structural reason German pilots could struggle to match the turn that followed such an entry, even when they could match the courage. The attacker, arriving with higher speed, could initiate a descending turn that remained controllable because the aircraft stayed above its stall margin, while the defender, entering the same turn from a lower energy state, approached stall sooner and was forced to either unload and widen the turn or accept a departure. That is geometry, not personality. The technical anchor was stall speed under load. Increase load factor, and stall speed rises, and a turn that looks identical from the outside is not identical inside the wing. American pilots did not celebrate this method in manuals. Many squadrons treated it as a personal tactic, tolerated when it worked and condemned when it did not. The aircraft itself would later receive design and procedural changes intended to reduce high-speed dive hazards because the underlying risk was real. A steep entry could deliver victory, but it also consumed airframe margin and demanded disciplined timing. Discipline meant a pilot had to know the exact moment to stop pressing the dive and begin recovery, even if the target still filled the windscreen, because beyond that moment the aircraft could refuse to obey. The technical anchor was structural load limit. In a pullout, G rises sharply, and the difference between 5G and 7G is not abstract. It is the difference between a controlled recovery and damage that accumulates invisibly until the next maneuver breaks something critical. Sicily in July 1943 created a setting where those limits did not stay separate. Flak forced altitude changes. Dust haze degraded sighting. Radio congestion delayed coordination. A pilot who waited for perfect information often waited too long. So the fight became a chain of forced choices, each one narrowing the next. In that chain, the dangerous dive entry functioned as a tool to erase intermediate steps. It reduced the number of decisions required between detection and firing, and it reduced the opportunity for the defender to construct a counter. The technical anchor was engagement range. If the attacker could compress the fight to a short-range snapshot, then the defender's advantages in climb planning, formation positioning, or extended turning became irrelevant because there was no time to use them. What emerges from the documented Sicily Air War is not a legend about an unbeatable man. It is a picture of a system that occasionally rewarded behavior that looked irrational from the outside. The same physics that made steep dives hazardous also made them decisive, because speed is both a threat and a stabilizer, and the margin between those roles is thin. Over Sicily, that thin margin was exploited by pilots willing to accept a narrower safety envelope in exchange for control over tempo. The technical anchor was margin management. When the margin is small, the pilot is not brave in the romantic sense. The pilot is operating a machine at the edge of its controllable state, where the smallest timing error converts advantage into catastrophe. The campaign moved on. Airfields shifted. Units rotated. The Mediterranean remained a laboratory of constraints rather than a gallery of personalities. But the logic of that dive-and-turn sequence persisted because it mapped onto the realities of escort, interception, and limited time over target. It worked best when altitude was available, when the pilot could see clearly, and when the target's own energy state was already compromised. It failed when any of those conditions broke, because the method did not create freedom. It spent freedom quickly to buy a brief window of dominance. The technical anchor was altitude as capital. Once spent in a dive, altitude cannot be recovered instantly, and a tactic built on spending altitude is only as repeatable as the altitude the environment continues to provide. That exchange rate between altitude and control became more unforgiving as the Sicily campaign progressed. By late July 1943, Allied fighters were increasingly tasked with low-altitude work, armed reconnaissance, road strafing, and interception of fighter bombers slipping through gaps in radar coverage. The vertical room that had made the steep entry survivable began to shrink. A dive that once started from 25,000 feet now began from 15,000 feet or less, and every 1,000 feet removed from the top compressed the recovery window disproportionately. The technical anchor was recovery gradient. As entry altitude fell, the pull-out arc steepened, and the same maneuver demanded higher instantaneous G to arrest descent before ground contact, stressing both pilot tolerance and airframe limits. This shift exposed a subtle but decisive limitation. The steep dive entry relied on precision, timing more than raw nerve. A pilot had to initiate recovery, not when the target was optimally framed, but when the aircraft's speed and attitude crossed a point beyond which control degradation would outrun intent. In practice, this meant abandoning shots that looked promising in favor of preserving the ability to fly the next second. The technical anchor was control lag. At high speed, the interval between control input and aircraft response lengthened just enough that a delayed decision could not be corrected in real time, turning a calculated risk into a locked trajectory. German pilots adapted unevenly. Some attempted to counter by initiating their own dives earlier, hoping to equalize entry speed and deny the Lightning its advantage. That response carried its own cost. To dive early was to surrender altitude without certainty of contact, and once altitude was lost, it could not be reclaimed quickly, especially under fuel constraints. Others chose aggressive head-on passes, trading deflection shots for the chance to break the attacker's timing. The technical anchor here was closure geometry. Head-on passes compressed time even further, reducing firing windows to fractions of a second and amplifying the role of convergence settings and gun harmonization rather than maneuvering skill. The P-38's concentrated nose armament mattered in this compressed regime, but it was not decisive by itself. What mattered was that a steep entry often forced a defender into a last-moment break that exposed the aircraft's flight path rather than its guns. A pilot who broke late did so at high load, increasing induced drag and bleeding speed at the worst possible moment. The technical anchor was induced drag under G. In a hard break, lift demand rises, drag rises with it, and speed decays faster than intuition suggests, especially at low altitude where true airspeed margins are already thin. American after-action analysis from the Mediterranean did not celebrate these encounters as clean victories. They recorded them as unstable engagements with high variance, where outcomes depended heavily on initial conditions. That assessment was accurate. The steep dive entry magnified differences in entry speed, altitude, and timing, turning small advantages into decisive ones and small errors into losses. The technical anchor was sensitivity to initial conditions. In such a system, repeatability declines, and tactics become situational rather than doctrinal. This sensitivity explains why the method never fully hardened into formal doctrine. Doctrine seeks reliability across a wide range of conditions. The Sicily environment offered a narrow slice, where the balance favored aggression, but even there the margin was thin. A moment of misjudged altitude, a gust that altered angle of attack, a brief loss of visual contact, and the same maneuver could end not in separation but in ground impact. The technical anchor was environmental variability. Wind, temperature, and visibility altered the effective envelope of the aircraft without warning, undermining assumptions made seconds earlier. As the air war over Sicily transitioned into the broader Italian campaign, the geometry shifted again. Mountainous terrain replaced coastal plains. Cloud layers thickened. Engagements fractured vertically, with fighters popping in and out of visual contact. In that setting, the steep dive entry lost some of its coercive power, because altitude could no longer be assumed to exist in a continuous block above the fight. The technical anchor was terrain-induced altitude discontinuity. When terrain rises into the combat volume, altitude ceases to be a uniform reserve and becomes fragmented, limiting how it can be spent. Yet the logic behind a maneuver did not disappear. It reappeared in modified form: shorter dives, earlier breaks, and an emphasis on first-pass advantage. The core idea remained intact. Control the moment of contact. Compress the opponent's decision space. Exit before the system's limits close. The technical anchor was first-pass lethality. If the first pass failed to produce separation or advantage, the probability of loss rose sharply, because the attacker's initial energy surplus would already be spent. What Sicily demonstrated in measurable terms was that air combat outcomes could hinge less on who could turn tighter or shoot straighter, and more on who could shape the engagement timeline. The steep dive entry was one way of doing that, not because it defied physics, but because it aligned with it under specific constraints. It turned altitude into a consumable resource, and time into the primary currency of survival. The technical anchor was temporal dominance. When one side dictates when the fight begins and how long it lasts, many other variables lose their power to influence the result. The pilots who used this method were not immune to its costs. Airframes accumulated stress. Maintenance crews found cracks and loosened fittings that did not appear in calmer squadrons. Fatigue built because flying at the edge of control demanded constant vigilance and offered little room for procedural comfort. The system absorbed those costs quietly, as systems often do, until conditions changed and the balance shifted again. The technical anchor was cumulative fatigue. Structural and human limits accumulated invisibly, and a tactic that worked repeatedly could still fail abruptly once those hidden margins were exhausted. That accumulation of hidden costs became visible only when pilots attempted to transfer the same behavior into environments that no longer supported it. By August 1943, as the air war pushed northward and missions stretched inland, the steep entry encountered a new constraint: navigation error. Over sea and coastline, orientation was stable. Inland, over broken terrain and smoke, a pilot descending at high speed had less visual reference to judge angle and height. The technical anchor was depth perception at velocity. At speeds exceeding 400 miles per hour, ground features expand nonlinearly in the visual field, and a misjudgment of even 1 second could erase the remaining recovery margin before the pilot recognized the error. This exposed a difference between tactical audacity and systemic compatibility. The maneuver depended on clean geometry, altitude above, space below, and a predictable horizon. When those conditions degraded, the same dive that once compressed the enemy's decision cycle now compressed the pilot's own. The technical anchor was perceptual compression. As speed increased, the rate at which visual information arrived exceeded the rate at which it could be processed, forcing decisions to rely on anticipation rather than confirmation. Anticipation worked only when the environment behaved as expected. German pilots, meanwhile, did not need to match the turn to counter the method. They needed only to deny the conditions that made it viable. In areas where cloud layers capped altitude or where terrain rose abruptly, Luftwaffe pilots began dragging engagements laterally, forcing American fighters into flatter pursuits where the Lightning's mass became a liability instead of an asset. The technical anchor was horizontal energy bleed. In sustained level turns, induced drag drained speed continuously, and without altitude to replenish it, the attacker's initial advantage evaporated. Reports from this phase describe encounters that ended not in clean separations, but in disengagements forced by fuel state or overheating. The steep entry no longer guaranteed a short fight. Instead, it risked initiating a merge that could not be cleanly exited. The technical anchor was exit feasibility. A tactic that cannot guarantee a viable exit path ceases to be a tactic and becomes a gamble, because the pilot commits before knowing whether separation will be possible. This distinction mattered to command planners. Escort doctrine prioritized predictability. Bombers did not benefit from escorts that could win a single spectacular engagement if that victory left the escort out of position or low on fuel. The system valued persistence over punctuated dominance. The technical anchor was coverage continuity. An escort that disengaged vertically and exited the combat area could leave bombers exposed minutes later, when replacement cover was not yet in place. As a result, the steep dive entry increasingly became situational rather than habitual. Pilots learned to recognize when the environment supported it and when it did not. This selectivity was itself a constraint because it demanded rapid assessment under stress. The technical anchor was decision bandwidth. A pilot already managing formation position, radio traffic, and visual scanning had limited capacity left to evaluate subtle envelope margins in real time. What remained consistent was the underlying lesson Sicily had imposed. Combat was not decided by exceeding limits, but by arriving at the limit later than the opponent. The pilot who forced the other aircraft to reach its control boundary first dictated the outcome, regardless of who possessed the theoretically superior machine. The technical anchor was boundary sequencing. When one aircraft hit its limit earlier, every subsequent option narrowed automatically. This lesson outlived the specific maneuver. It influenced how pilots thought about entry angles, closure speed, and the cost of hesitation. Even when dive angles moderated and recovery margins widened, the emphasis on seizing temporal advantage remained. The steep entry had been an extreme expression of a broader principle, that in air combat, time is often more decisive than geometry. The technical anchor was time to decision. The aircraft that demanded an immediate response from its opponent gained leverage, simply by forcing that response to occur under pressure. By the end of the Mediterranean campaign, the Lightning's reputation had stabilized. It was no longer judged primarily by its ability to turn or climb, but by its capacity to control the vertical dimension when conditions allowed. The madness label faded not because the risks vanished, but because the risks were better understood. The maneuver was no longer mysterious. It was bounded. The technical anchor was envelope awareness. Once pilots internalized where the edge lay, they could approach it deliberately rather than stumble into it by accident. Still, the episode resisted clean categorization. It did not fit neatly into manuals, and it did not scale uniformly across theaters. Over Sicily, it had thrived because the system briefly aligned. Altitude availability, predictable weather, and opponents constrained by fuel and terrain. When those variables shifted, the method receded. The technical anchor was systemic alignment. A tactic that depends on multiple external conditions cannot dominate once those conditions diverge. What Sicily ultimately revealed was not a story of daring individuals rewriting the rules, but of a rule set with narrow tolerances being exploited at exactly the right moment. The steep dive entry worked because it treated limits not as walls, but as thresholds that could be approached asymmetrically. One side crossed them under control, the other crossed them reactively. The technical anchor was asymmetric limit crossing. When one aircraft reaches a limit by choice and the other by necessity, the outcome is already constrained before weapons come into play. The air war moved forward, and newer aircraft with improved high-speed control reduced the need for such edge-bound behavior. Compressibility would be addressed through design, not courage. But the memory of that narrow window over Sicily remained embedded in pilot culture as a cautionary reference point, not as an instruction, but as a demonstration of how quickly advantage can be created and destroyed when machines, humans, and environment intersect at the edge of control. That intersection between machine, human, and environment also exposed how fragile tactical reputations could be once stripped of context. Pilots remember the dive and the turn, but the decisive factor often lay earlier, in positioning decisions made minutes before contact. A Lightning that began the encounter even 2,000 foot lower than planned lost the option to convert altitude into time. And without that conversion, the steep entry collapsed into an ordinary pursuit with none of its coercive power. The technical anchor was initial altitude offset, a small deficit at the start propagated through every subsequent maneuver, narrowing choices until only disengagement or loss remained. This dependency explains why similar attempts sometimes failed under apparently identical conditions. Two pilots could execute the same dive angle and recovery technique, yet arrive at different outcomes because their entry states were not truly equal. Speed differed by tens of mph. Altitude differed by hundreds of feet. The difference was invisible in recollection but decisive in physics. The technical anchor was state vector divergence. Once the aircraft states diverged, even slightly, the same control inputs produced different trajectories, and the pilot who assumed symmetry discovered it did not exist. Maintenance records from Mediterranean units quietly reflected this reality. Aircraft flown aggressively showed higher rates of control rigging adjustment, tailplane inspection, and elevator linkage wear. None of these failures announced themselves dramatically. They accumulated until control feels subtly changed, increasing pilot workload and shrinking tolerance for error. The technical anchor was mechanical slack. As tolerances widened, response became less predictable, forcing the pilot to react earlier and with greater precision to achieve the same outcome. That mechanical drift interacted with human fatigue. Flying repeated sorties at the edge of the envelope demanded sustained concentration. Small lapses mattered more when margins were thin. A pilot who misjudged closure by a fraction of a second, or who hesitated during recovery, could not rely on excess performance to compensate. The technical anchor was cognitive depletion. As fatigue increased, reaction times lengthened, and the very tactic designed to compress the opponent's decision cycle began to compress the pilot's own. Commanders noticed the pattern indirectly. Units that relied heavily on high-intensity vertical attacks reported uneven effectiveness across sorties, with spikes of success followed by periods of caution. This oscillation was not psychological mood. It reflected the system's attempt to self-correct. When losses or near misses occurred, pilots widened margins. When conditions again aligned, margins narrowed. The technical anchor was risk elasticity. Tactics expanded and contracted in response to recent outcomes, not because of doctrine, but because of lived constraint. The Luftwaffe's experience mirrored this dynamic from the opposite side. German pilots learned that attempting to mirror the Lightning's vertical behavior often accelerated their own losses. Those who survived longest tended to deny verticality altogether, breaking early and dragging fights into regimes where the P-38's advantages dissipated. The technical anchor was engagement shaping. By choosing when not to fight vertically, defenders preserved options even if they surrendered the initiative. This asymmetry reinforced a broader operational truth. Air combat did not reward universal solutions. It rewarded localized dominance inside specific envelopes. Over Sicily, the envelope briefly favored steep entry and rapid separation. Elsewhere, it did not. The technical anchor was envelope locality. Performance advantages existed only within bounded regions of altitude, speed, and geometry, and crossing out of that region inverted their effect. The historical record preserves this episode not through proclamations, but through patterns. Shifts in engagement altitude, changes in separation behavior, and the gradual moderation of extreme dive angles as circumstances evolved. These patterns reveal adaptation rather than triumph. The steep entry was not abandoned because it was disproven. It was constrained because its prerequisites became rarer. The technical anchor was prerequisite scarcity. As the campaign matured, the conditions that enabled the tactic occurred less frequently, reducing its practical value without negating its logic. What remains instructive is how quickly perception lagged behind reality. Labels like madness persisted even after outcomes demonstrated effectiveness, because institutional understanding updated more slowly than combat practice. Manuals lagged sorties. Reports lagged experience. The technical anchor was informational latency. Decisions about what was acceptable were made with data already outdated by the time it reached decision-makers. In this gap between practice and policy, individual pilots navigated by feel rather than instruction. They sensed when altitude, speed, and visibility aligned and when they did not. That sensing was not mystical. It was a learned sensitivity to gradients. How fast the ground rose, how quickly speed built, how early controls stiffened. The technical anchor was gradient awareness. Pilots learned to read rates of change rather than absolute values because rates signaled danger sooner than numbers. By the time the Mediterranean Air War gave way to broader Allied dominance, the steep dive entry had become one of several tools rather than a defining behavior. Its legacy lay less in replicated maneuvers than in altered priorities. Pilots valued initiative that constrained the enemy's timeline. They sought to decide fights before complexity multiplied. The technical anchor was complexity suppression. By shortening engagements, pilots reduced the number of interacting variables that could spiral beyond control. This legacy did not end with the P-38. Later aircraft, designed with better high-speed handling, embedded the same principle structurally rather than tactically. They reduced the penalty of speed and expanded recovery margins, allowing pilots to apply vertical pressure without flirting as closely with disaster. The technical anchor was design-mediated margin. Engineering absorbed risks that earlier pilots had managed manually, shifting the burden from judgment to structure. Yet Sicily remains a reference point precisely because the balance was so precarious. The maneuver worked not because it was safe, but because it was timely. It exploited a moment when opponent limitations, environmental conditions, and aircraft characteristics briefly overlapped. Outside that overlap, it lost coherence. The technical anchor was temporal convergence. When multiple constraints align in time, they create opportunities that vanish as soon as alignment breaks. The story therefore resists simplification. It is neither a cautionary tale nor a celebration. It is an illustration of how warfare rewards those who recognize when a system is momentarily vulnerable to pressure applied along a specific axis. Over Sicily, that axis was vertical, steep, and brief. Once recognized, it could be exploited. Once conditions shifted, it could not. What followed was not consolidation, but dissipation. As Allied air power thickened over Italy and the Mediterranean narrowed under radar coverage, The opportunity to impose surprise through extreme vertical entry diminished. Detection ranges increased. Intercepts began earlier. Fighters met each other with less altitude asymmetry and more mutual awareness. The steep dive lost its element of coercion because it no longer arrived unannounced. The technical anchor was early warning latency reduction. When detection moved from visual to instrument-supported timelines, the attacker's ability to compress the opponent's decision window eroded before contact even began. This change reframed the maneuver's cost-benefit balance. Without surprise, the dive still consumed altitude, still stressed airframes, and still demanded precise recovery, but it no longer guaranteed an opponent caught mid-decision. Instead, defenders could anticipate the entry, time their breaks earlier, and shape the merge on their terms. The technical anchor was anticipatory maneuvering. A defender who reacts before the attacker commits can spend energy deliberately rather than waste it reactively, preserving control authority deeper into the fight. For the P-38, this meant that vertical aggression increasingly required coordination rather than individuality. A single aircraft diving steeply could be countered. A pair, staggered in altitude and timing, could still impose dilemmas. But coordination itself introduced friction, radio delay, visual separation, and the risk of misalignment at speed. The technical anchor was synchronization tolerance. At high closure rates, even small timing errors between wingmen could collapse mutual support, leaving each aircraft temporarily isolated. Operational planners absorbed these realities unevenly. Some squadrons leaned toward disciplined escort geometry, prioritizing bomber proximity over pursuit. Others retained aggressive interception profiles, accepting dispersion as the price of initiative. Neither approach was universally superior. Each solved one constraint by aggravating another. The technical anchor was trade space saturation. When multiple constraints compete, improving one dimension inevitably degrades another, and no configuration eliminates cost. The memory of Sicily nonetheless persisted because it clarified a principle that outlasted the specific aircraft. It showed that aerial combat systems are most vulnerable not at their weakest points, but at their transition points, where one regime hands off to another. The steep dive exploited the transition between cruise and defensive maneuver, between awareness and reaction. The technical anchor was regime transition instability. Systems are least stable when shifting modes, and pressure applied precisely at that shift yields disproportionate effect. This understanding quietly informed later tactics, even as aircraft changed. Pilots sought to engage at moments of transition, during climbs, during turns, during reformation, during fuel checks. The dive was no longer necessarily vertical or extreme, but the intent remained to strike when the opponent's control logic was mid-adjustment. The technical anchor was control state mismatch. When one aircraft operates in a stable state and the other is mid-transition, symmetry breaks automatically. Historical reconstruction often struggles to capture this, because reports emphasize positions and outcomes rather than timing. Yet timing was the decisive variable. Who committed first? Who delayed? Who forced the other to move before being ready? Over Sicily, the steep dive entry forced that movement brutally and early. Later, subtler methods achieved the same effect with less risk. The technical anchor was commitment timing. Once committed, an aircraft sheds options rapidly, and a tactic that forces premature commitment reshapes the entire engagement. The label of madness lingered precisely because observers focused on the visible risk rather than the invisible calculation. The dive looked reckless because its failure mode was obvious and violent, while its success mode appeared effortless and therefore misleading. The technical anchor was failure salience. Humans overestimate the likelihood of vivid failures and underestimate the discipline required to avoid them, especially when success leaves little trace. By the end of the war, formal doctrine would emphasize envelope awareness, mutual support, and controlled aggression. It would not instruct pilots to dive vertically into uncertainty, but embedded within that doctrine was the residue of lessons learned earlier, under less forgiving conditions. The steep entry had served as an extreme experiment, mapping where the edge lay and what could be extracted from it before control dissolved. The technical anchor was boundary mapping. Only by approaching a limit can a system learn where it truly resides. Sicily's air battles therefore occupy an ambiguous place in history. They were neither anomalous nor repeatable at scale. They were moments when constraint, opportunity, and judgment briefly aligned. The pilots who survived them did not carry forward a recipe. They carried forward a sensitivity to timing, margin, and the cost of delay. The technical anchor was sensitivity retention. Even when the maneuver vanished, the perception it trained remained. As the conflict progressed and technology absorbed more of the burden, the need to operate so close to disaster diminished. Control systems improved. High-speed handling stabilized. Recovery margins widened. The system learned. But that learning was cumulative, built on earlier periods when judgment substituted for engineering. The steep dive over Sicily belonged to that earlier phase, when advantage was carved not by superior machines alone, but by the willingness to exploit a narrowing window before it closed. The enduring significance lies there, in the recognition that warfare often advances not through steady improvement, but through brief exposures of vulnerability that demand immediate exploitation. Miss the window, and it disappears. Enter it too late, and it collapses inward. Over Sicily, the window was vertical, fleeting, and unforgiving, and for a short time it could be used to decide fights before they fully began. Seen from distance, the episode contracts into scale. What appeared in the summer of 1943 as a peculiar habit of certain P-38 pilots resolves, with time, into a transitional moment in air warfare when human judgment was still required to bridge gaps that engineering had not yet closed. The steep dive over Sicily was not a doctrine, not a secret technique, and not a personal trademark meant to be imitated. It was a symptom of a system under strain, adapting faster at the cockpit level than at the institutional one. The technical anchor at this scale is technological lag. Aircraft performance, pilot training, and command doctrine did not advance in lockstep, and the resulting gaps were temporarily filled by behavior that accepted risk as a substitute for margin. Historically, this matters because it clarifies how air combat evolved between early war improvisation and late war standardization. In the early years, advantage was often extracted through deviations that exploited narrow envelopes before they were formally understood. By the end of the war, those envelopes were widened or eliminated through design. Boosted controls, dive recovery flaps, refined airfoils, and clearer operating limits. What had once required nerve and timing became embedded in structure. The technical anchor here is institutionalization of margin. Once margins are engineered, behavior no longer needs to trespass so close to failure to achieve effect. The Sicily fights sit precisely at that hinge point. They occurred after pilots had learned enough to sense where danger lived, but before machines had been redesigned to make that danger irrelevant. In that interval, success depended on the ability to recognize when the system could be bent without breaking. This was not intuition divorced from analysis. It was applied understanding of rates, gradients, and thresholds learned through repetition under pressure. The technical anchor is experiential calibration. Pilots calibrated themselves against their machines in combat, refining an internal model more detailed than any checklist. German inability to match the turn was therefore never a question of courage or competence. It was a reflection of structural asymmetry. The defending pilot was forced into reaction. The attacking pilot chose commitment. One crossed limits deliberately. The other was pushed into them unwillingly. At scale, this distinction recurs across warfare. Systems that dictate tempo impose costs that cannot be avoided, only paid in different currencies. The technical anchor is imposed tempo. Whoever controls the clock controls which limits are encountered first. As the war progressed, the Mediterranean became less permissive, and the behavior faded, not because it had been disproven, but because the conditions that made it efficient no longer recurred with the same frequency. That disappearance itself is instructive. Effective tactics do not necessarily endure. They expire when the environment that sustained them changes. The technical anchor is environmental dependency. A method that relies on specific alignments dissolves once those alignments disperse. In retrospect, the value of the episode lies less in the maneuver than in what it reveals about adaptation under constraint. It shows how combat systems generate temporary solutions that appear irrational until their context is reconstructed. It also shows how institutions eventually absorb those lessons, translating risky behavior into safer design and individual judgment into standardized capability. The technical anchor is translation from behavior to structure. What is first learned through danger is later preserved through engineering. Sicily, then, is not remembered for a single dive or a single turn, but for what it exposed, that the decisive variable in air combat was often not performance alone, but timing under pressure. and that pressure could be manufactured by compressing the opponent's options faster than doctrine anticipated. For a brief period, that compression took the form of near-vertical commitment and violent recovery. Later, it would take quieter forms, embedded in systems that no longer required pilots to gamble so openly with the edge. The air war moved on, as wars do. But the logic uncovered there did not vanish. It became part of the accumulated understanding that shaped subsequent aircraft, training, and expectations. The steep dive over Sicily was one expression of that logic, visible precisely because it operated so close to failure. In that proximity, the structure of the system was revealed, and once revealed, it no longer needed to be approached in the same way again.